Welcome dear students. In this lecture we are going to talk about the electrophilic substitution reactions of the benzene, and these are the favorite reactions of the benzene, and benzene prefers electrophilic substitution reactions over electrophilic addition reactions. In this lecture you will also find the answer to this question, that why the electrophilic substitution reactions are the favorite reactions of the benzene. Let us first see what is meant by the electrophilic substitution reactions. These are the reactions in which an electrophile replaces one of the hydrogens of the benzene ring, and you will get the mono substituted derivative of benzene, and that hydrogen then combines with the nucleophile. Now my dear students, what is the mechanism of electrophilic substitution reactions of the benzene? We are going to talk about the general mechanism. The first step is the generation of strong electrophile. As we have already discussed that benzene has delocalized pi electrons, it has 5 resonance structures, it has high resonance energy, so benzene is highly stable. That's why the weaker electrophiles, they cannot attack the benzene ring. So the first of all, you will have to generate the stronger electrophile, and for the generation of stronger electrophile, my dear students, the reagent reacts with catalyst of the reaction. Nucleophile combines with catalyst. A stronger electrophile is generated, and nucleophile goes with the catalyst. So catalyst plays an important role in the generation of the stronger electrophile. You can see that here this electrophile will be partial positive, but in this case the complete positive charge is there on electrophile. So an electrophile with partial positive charge, that will be relatively weaker, but an electrophile with complete positive charge, that will be a stronger electrophile. Now, my dear students, once the stronger electrophile is generated, the second step should be the attack of stronger electrophile on benzene. When the stronger electrophile attacks the benzene, this is one of the resonance structure of benzene, and when it will attack the benzene, my dear students, now the carbonium ion, or you can say carbocation, is generated, and this carbocation is then resonance stabilized. You know that the positive charge along with the pi electrons, that can resonate in the ring. So in this case, my dear students, this pi bond will be shifted here, and the location of the positive charge, that will be changed. It will be now on this carbon, and again dear students, the double bond changes its location, and due to change of its location, the positive charge that will also change its corner. And now, my dear students, this carbonium ion is resonance stabilized basically. After the formation of this carbonium ion, now, my dear students, the third step should be regeneration of catalyst. As you know, that catalyst increases the rate of reaction without being used. So in this case, again, the catalyst that should not be used, and the final step will be that the nucleophile that was attached to catalyst, now it will take the hydrogen with it, and my dear students, the bond between carbon and hydrogen that will be shifted inside the ring. In this way, this catalyst that moves out unchanged. My dear students, the hydrogen goes with nucleophile, and now again this product will be obtained, that is the mono-substituted derivative of the benzene. So it was the general mechanism in which, first of all, a stronger electrophile is generated with the help of the catalyst. Then this stronger electrophile attacks the benzene ring to form the carbonium ion or carbocation. That carbocation is resonance stabilized, and finally the nucleophile takes the hydrogen of the benzene ring, and the catalyst is regenerated and mono-substituted derivative of the benzene is created. Now, my dear students, let us answer to that question, that why electrophilic substitution reactions are the favorite reactions of the benzene. If we can compare the electrophilic reactions, addition reactions of the alkene with benzene, my dear students, the electrophiles, they also attack the double bond of the alkenes, and in that case carbonium ion is generated. And in the next step, then my dear students, this carbonium ion is easily attacked by some nucleophile. As a result of this addition reaction, then this unsaturated molecule that is changed to the saturated product. In case of benzene, the carbonium ion is generated, and in case of alkenes, carbonium ion is generated. So this step is common in case of alkenes and benzene, but the similarity ends here, because in case of alkenes, the nucleophile can easily attack the carbon that is positively charged, and it can form a saturated product. But in case of benzene, look at the last step. This last step, my dear students, in case of benzene, the nucleophile cannot attack the positively charged carbon of the benzene, and it will not be added to the benzene ring, because if it is added to the benzene ring, aromaticity of benzene will be lost. And benzene loves its aromaticity. Benzene will never like to lose its aromaticity. That's why the nucleophile will not be able to attack on the positively charged carbon. Rather, it will just take hydrogen with it. And my dear students, catalyst is regenerated, nucleophile goes with hydrogen, and the aromaticity of the benzene remains intact even in its monosubstituted product. Aromaticity means the alternate pi bonds. So benzene prefers electrophilic addition reaction, electrophilic substitution reaction over electrophilic addition reactions, because during electrophilic substitution reactions, the aromaticity of the benzene remains intact, but during electrophilic addition reactions, the pi bonds are completely vanished and the aromaticity of the benzene is lost. So benzene loves its aromaticity, therefore benzene will never like to lose its aromaticity. That is why the benzene loves to show electrophilic substitution reaction rather than electrophilic addition reaction, even though it is highly unsaturated. The key point is the aromaticity of the benzene should remain intact, as benzene loves its aromaticity. So that was the general mechanism of the electrophilic substitution reaction of the benzene, how many steps it has, how the carbocation is resonance stabilized. Next time we will come up with some examples of the electrophilic substitution reactions. I hope so. The lecture will be understandable for you people. In case you find any problem, you can ask in the comment section. Till then, take care.